We study X19NQ, driven damped harmonic oscillation. So NQ for X19, it's this PDF file can be downloaded if you visit kpop.org and scroll down to reach X19. If you click this, you will find X19, the original version. And if you click here, you
이번
will find
시간에는 드립
the lecture given in Korean and English.
In the previous class, we studied the simple harmonic oscillation.
And then there is a checkpoint. There are many problems. There's an application. And then there is a queue. There are few problems, serious problems. And then N is for the preparation of X19Q. So you can also visit our website. This is YouTube. Oh, okay. You will find okay, various contents regarding physics education. In the playlist, you'll find our the K-pop quiz guide. This is a XQs, all of the XQs and XNQs can be found there. There are ESA, Escape from Scientific Absurdity, and Y series for the second semester, General Physics 2, and many others you can find, including classical mechanics or quantum mechanics or relativistic quantum mechanics as well. Okay, let's go. X19NQ, in here we focused on the phase analysis in the multiplication or linear combination of a trigonometric function. The relation can be found if you closely look at the structure of the rotation matrix in two-dimensional Euclidean space, or it can equivalently derive by making use of Euler's formula or e to the I theta. Okay, you can also click this to find the YouTube file after recording this lecture, and the kpop.org can be directly accessed, and you can subscribe K-pop YouTube homepage. All right, let us consider the rotation on the xy plane. The original unit basis vector for the Euclidean space are E1 hat and E2 hat. We'd like to rotate these two vectors to obtain by an angle of theta about the z-axis to obtain E1 prime and E2 prime. As we already studied, rotation matrix R is defined by cosine sine and minus sine cosine. Perhaps you have already forgot how to derive this, the simplest way to derive this is the transformation of E1 to E1 prime. If I rotate this vector, the Cartesian coordinate will be 1, 0, and after rotation, it becomes a cosine theta and sine theta. If you write these coordinates as a column vector, then the coordinates in terms of original coordinate system, original basis vectors, it will be cosine and sine. So as a result, the unit vector, this point, unit vector along the x-axis transforms into cosine theta and sine theta. As a result, if you multiply 1, 0 to this matrix, you will get this column. First column will be this. What about the second case? If I rotate this E2 hat, whose Cartesian coordinates are 0 and 1. After the rotation, you will find x coordinate is minus sine theta and y coordinate is a cosine theta. As a result, if you rotate this vector, your final result will be minus sine theta and cosine theta. This should be read off from the matrix. If I multiply 0, 1 to here, then I can collect the second column of this rotation matrix. Another way to reconstruct this is by making use of the completeness relation. So E1 hat vector can be expanded in terms of E1 hat, E1 prime and E2 prime. The completeness relation states that this one should be expanded in such a manner. And we find the scalar product between E1 and E1 prime. This is cosine theta. And E1 and E2 prime. E1 and E2 prime, that is minus sine theta. So we can obtain the first row of this rotation matrix. In a similar manner, I can rewrite E2 as a linear combination of E1 prime and E2 prime. So completeness relation shows that it is E1 prime and E2 prime. The scalar product between E2 and E1 prime, E2 and E1 prime, because it is 1/2 of pi minus theta, it should be sine theta. And then E2 dot E2 prime, E2 dot E2 prime, because this angle is a theta, the value is a cosine. As a result, we can reproduce the second row of this rotation matrix. In general, matrix multiplication is not commutative. However, if you keep the axis of rotation invariant, then any two series of rotation commute. For example, I first rotate a vector by an angle, this vector, by an angle of theta 1, and I obtain the resultant vector here. And then I rotate about the z-axis by theta 2 again. Then this is the final value. So this angle is identical to the sum of the two angles. I can flip the order and rotate this original vector by theta 2 first and theta 1 next. We arrive at the same point. So this one states that if I rotate the two-dimensional vector about an axis, fixed axis, in series by theta 1 and then theta 2, or theta 2 then theta 1, the two result should be the same. As a result, if I rotate first by theta 1 and then theta 2, this whole process can be expressed as a single rotation matrix. Rotate this vector about the z-axis by theta 1 plus theta 2. That is equivalent to the product of two rotation matrices by theta 1 and theta 2, theta 2 first and then theta 1 next. As a result, we can prove this addition formula for trigonometric functions. Let's see. Rotation matrix about the z-axis on the two-dimensional Euclidean space can be expressed as a product of R alpha and R beta. As we have already stated, it must be the same as a single rotation matrix by an angle of the sum. Because we have already obtained a single rotation matrix, I substitute alpha plus beta for these angles, theta. The result is a cosine sine minus sine cosine with the arguments all with alpha plus beta. Let us try to compute this as a product of the two matrices. Rotation matrices are alpha and R beta. Direct multiplication of two matrices can be made by multiplying this row and column, row and column, row and column, and row and column. So 1 element is the product of the first row of the first matrix and the first row of the second matrix. If I multiply two matrices, we multiply A1, A2, B1, B2, then A1, B1 plus A2, B2. Who told you? Who told you? Descartes told you it originates from the scalar product of two vectors, and we have written this Cartesian components of this vector as a row vector, and Cartesian components of this a B vector, B1 and B2 as a column vector. And this was A1, B1, A2, B2. Because of what? Because of the orthogonality relation between any two unit Cartesian basis vector. That is either 1, that I equals j, or 0, when I is not equal to j. Okay, so as a result, I can multiply this and this, cosine, cosine, minus sine, sine. And then this element, cosine, sine, minus, sine, cosine, minus. What about this? This and this, sine, cosine, cosine, sine. Last one, sine, sine, negative, sine, sine, negative, cosine, cosine, positive. If you investigate the structure, this one, they are the same. They are the same. Just like this one and this one. So I can find the relation cosine alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. Next one, this one and this one, they are the same except that their signs are different. Just like that. So I can compare these two to find that sine alpha plus beta equals sine cosine, cosine sine. So I have reproduced the addition formula for the trigonometric function by making use of the fact that the product of rotation matrices about a single invariant axis of rotation commute. Next, we consider this case. R theta, if I multiply R theta twice, the result is R2 theta. Because if I substitute alpha and beta, it must be alpha plus beta. If I multiply R2 theta and theta, my result will be the sum, that is R3 theta. Therefore, if I multiply theta by n times, the result is exactly Rn times theta. What about replacing theta with theta over n? So 1/n of theta. In that case, 1/n of theta, repeated multiplication of this by n times will be Rn times theta over n. They cancel to find that R theta. And this result is not an approximate value, but an exact value. All right, that's fine. Why don't we take the limit, insert the limit as n goes to infinity? In that case, we'd like to see the structure cosine, sine, minus sine, and cosine with the same argument. We remember that sine of x therefore it begins with x, 3 factorial x cubed, and so on. Cosine of x therefore it should be, and so on. As a result, I can express this matrix as a power series of 1 over n. Would you like to see what happens? So we shall find this rotation matrix can be expressed in this form. Let's see. By making use of this expansion, power series expansion of this sine and cosine. Real part of the e to the I theta is the cosine. You know, this a plus I bi. This is called real part of the complex number z. And this is called the imaginary part of the complex number z. As we already stated in here, power series expansion of a cosine and sine are given in here. So I can substitute these values in this matrix. By the way, cosine has the theta independent term. I mean the n independent term. That is unity for the diagonal element. And then there is a linear term, theta over n, appears in the off-diagonal terms. So off diagonal elements has a theta over n, and there's a asymmetric matrix. The diagonal elements all vanishes, and they are unity except that the signs are different. And then we can make a further expansion, power series expansion in powers of 1 over n, and we denote any other terms of order 1 over n squared and higher. If you take the limit as n goes to infinity, this expression collapses into limit n goes to infinity 1 plus theta over n, a matrix to the nth power. You know what I mean? We learn by making use of the binomial expansion, we have proved that this part completely collapses to zero as n goes to infinity. So, in that case, this one can always expressed as an exponential form, n, exponential form. And we do not know how to express the exponential of a matrix. However, we do know how to find the power series expansion of theta of this matrix. So that is k factorial theta k a k. So this is a matrix. This is a real number representing an angle. Therefore, we generalized the definition of the exponential function to include the arguments as a matrix. And the matrix exponential is always expressed as a power series expansion as long as its series converges to a certain value of matrix. We remember this expansion is possible because of this relation. Don't forget to reproduce the exponential function as a power series. Next, we evaluate the series of this exponential theta a. We remember theta a is this matrix. We square this, multiply this. Okay, so we have minus 1. Multiply this, 0. Multiply this and this, 0. And then we have again minus 1. This is a minus times identity matrix. As a result, if I repeat the multiplication by even numbers of a, it is minus 1 to the k identity. Odd powers, then even powers give minus 1 to the k and an additional single matrix A. It is very similar to the summation of exponential I theta, where I squared equals minus 1, I to k equals minus 1k, I to k plus 1 is a minus 1k I. And that was used to derive the Euler's formula, cosine theta, sine theta. Okay, identical method is applied to obtain the separation of even powers and odd powers. Even powers gives cosine and odd powers gives a sine. In the expansion of e to the I theta, we had an additional factor of I. In here, instead of I, we have additional factor of matrix A. And matrix A is this. And what is this? This is identity matrix. All right, I can replace this one as a cosine theta, and replace this one as a sine theta, and multiply two, these 2 by 2 matrices. As a result, exponential I to the A is a linear combination of this. And even if we do not know the series sum is cosine and sine, forget about it. We can reproduce this. Anyway, let us say it is f of theta, and this is g of theta. Substitute f minus g. I don't know what it is. However, I can identify that this one began. This was obtained by rewriting the rotation matrix R theta, and we already know that what it was. It was this. So even if I do not know what this is, I do know what the rotation matrix is. Therefore, by identifying these two matrices, I can identify the sum as a cosine and sine, even if you were ignorant of this power series expansion of cosine and sine. So this was another proof of the power series expansion of cosine and sine by making use of the rotation matrix. We can also apply Euler's formula to find the addition formula for the trigonometric functions. Okay, e to the I alpha, e to the I beta can be multiplied, and we make use of Bernoulli definition, and this is e to the 1 plus I alpha over n to the n. We take the limit as n goes to infinity, and this one can also be expressed in this manner. For simplicity, we choose so n prime equals n plus delta. We assume delta is a positive, but it doesn't matter. But for simplicity, n prime is taken to be n plus delta. All right, then we can combine these two as long as the two powers are the same. And we have a remaining piece that doesn't match. Because they are in a simple power, I can expand the product. In addition, the expansion will give I squared alpha beta over n squared. However, this term plus 1 over n squared term vanishes as n goes to infinity, as is already given in here. Therefore, this one becomes nothing but this. So I can reproduce the law of exponent. By the way, we have neglected this term because we have treated this one to be a finite value, and then as n prime goes to infinity, it disappears. All right, because of this, the product of the two exponential I alpha and I beta is e to the I alpha plus beta, and we know I alpha is a cosine alpha plus I sine beta. Therefore, this product is a cosine alpha plus beta and sine alpha plus beta. We substitute this Euler's formula for each factor and expand them and make use of the fact that I squared is minus 1. We have cosine cosine minus a sine sine as a real part, and imaginary part will be cosine alpha sine beta. Cosine alpha sine beta, sine alpha cosine beta. This is another way to prove the addition formula for the trigonometric functions. That's it for today.